Let's try to understand the concept of p-n junction diode. p-n junction diode is a basic semiconductor device. Okay, it's a basic semiconductor device which is formed of p and n-type semiconductor brought together. When p and n-type semiconductor are brought together in a single crystal, then p-n junction diode is formed. And the boundary between the two regions, the p region and n region, we call it p-n junction. So they are found by different ways, the p-n junction diode. One of the ways is like we first cut the n-type semiconductor like germanium, okay, into small slices that we can call wafers, okay, and that n-type semiconductors, n-type wafers, small thin slices, if you keep the aluminium and if you heat it over 600 degrees Celsius temperature, then the aluminium will diffuse into the n-type semiconductor. So p-type, and aluminum is p-type semiconductor. So what is happening? A p-type semiconductor is formed on n-type semiconductor. This is one of the ways of forming the p-n junction diode. So in p-n junction diode, what is basically happening? So there is a p region and there is an n region. If you bring them together by any method, then so that the boundary between them, we call it junction, p-n junction, and this whole crystal we call it p-n junction diode, which is the basic semiconductor device. Let's try to understand what happens here in the p-n junction, okay, diode. So you know, in p-type semiconductor, the majority charge carriers are holes, positive charge holes. In case of n-type semiconductor, the majority charge carriers are electrons, that we know. So when the p-type semiconductor and n-type semiconductor are brought together, when they are formed in a single crystal, then the electrons from the n region has higher concentration compared to the electrons in the p region. So electrons from the n region starts diffusing towards the p region. And in case of p region, the holes in p region is more compared to the holes in n region. So holes from the p region starts diffusing to the n region. Let's try to recapitulate that what we have learned in the last video. In the p region, this is p-type semiconductor and this is n-type semiconductor. In p-type semiconductor, now concentration of hole is more compared to the electron here. So holes are the majority charge carriers and electrons are the minority charge carriers. You can see these are the holes, but you can see a negative charge here also. What is this negative charge? If you remember how to make p-type semiconductor, to make p-type semiconductor, usually we have germanium or silicon semiconductors, which is pure semiconductor, which has 4 electrons on the valence shell. But if you use trivalent impurity like aluminum or boron, so it has only 3 electrons in the outermost shell. So it can form 3 covalent bonds with the 3 of the germanium atom. Okay, and one of the space in the aluminum or boron atom is empty. Okay, and because of that, what happens? The electron and this aluminum or boron atom can act as a acceptor energy level. Let me show you the picture. Here you can see this is the energy level corresponding to trivalent atom, that is boron or aluminum here. Okay, so electrons will easily go to the acceptable levels. And once the electron go to the acceptable levels, this acceptor atoms like boron or aluminum, they become negatively charged, and the more number of holes will be created here, because more number of electrons can easily go to these acceptable levels, because this acceptable levels is very close to the valence band. So here, therefore, this behaves as a p-type semiconductor that I have discussed before also in the previous video. So here the negative charge that you can see is the negative charge of the acceptor atoms. Okay, it may be boron, it may be aluminum. So that's what you see in the picture over here. This negative charge is the charge of the acceptor ion. Okay, so it is boron B minus or it is aluminum minus, or one of these it can be. Okay, this is the holes in the valence band. Similarly, if you remember in n-type semiconductor, we have pentavalent as impurity atom. In case of pentavalent as impurity atom, if you add them, then they act as a donor at energy levels. Here you can see, suppose we use uh, arsenic as a pentavalent atom impurity, then for arsenic we will have this as a energy level, donor energy level. So here what happens, that electron from this energy level can easily go to the conduction band. Okay, once the electron from here goes to the conduction band, this donor atoms becomes donor ions. They become positively charged donor ions. Okay, arsenic plus or phosphorus plus they become. So that's what is shown in the figure. Here you can see the positive charge is the donor ion, which is phosphorus plus or arsenic plus. Okay, and these black dots are the electrons in the n region. In the n region, the majority charge carriers are the electrons, and this plus is the plus phosphorus or plus arsenic, the donor ion. Now, as I told you, because of the concentration difference, the electrons from the n region start moving towards the p region, and the holes from the p region moving towards the n region. So in the junction, what happens, these electrons and this hole recombine. Once they recombine, they neutralized. Okay, so once this electron goes from here to here and combine with the hole, they neutralize, but they leave behind the positive charge here. See, suppose there was one electron over here, this electron went to this side, and there was one hole over here, this hole moved towards this side. So this electron and this hole recombine, and they are neutralized and vanished, but this positive charge and this negative charge is left behind there. Here also, one electron and one holes, when they come to the junction, they recombine and they leave behind the positive charge and negative charge. So you can see on the right hand side, since the electrons are coming towards p region and the holes are coming towards n region, so on the left hand side you can see when the electrons are left from here, it leaves behind the positive charge ions, and once the holes moves towards the right hand side and get neutralized, it leaves behind the negative charge ions. So these are positive and negative charge immovable ions. Okay, so these positive and negative charge immovable ions create an electric field over here, internal electric field, because the electric field is always directed from positive to negative. So this will be the direction of the electric field set up, okay, after the diffusion, and that will happen in the junction because the electrons and holes will recombine in the junction, and once they recombine, the electrons will leave behind the positive charge on the right hand side and the holes leave behind the negative charge on the left hand side, and there is a electric field set up in between the junction. That now this electric field, this will happen until and unless the electric field which is generated here becomes strong enough to stop this further diffusion. Now see, if this electric field is strong enough, then these holes will no longer be diffused towards this region because this hole will be repelled by the positive charge. Similarly, these electrons will no longer be diffused towards this side because this electron will be repelled by the negative charge. So this electric field will be this the accumulation of positive charge and negative charge on the junction will be there as long as there is a diffusion going on. Okay, once the electric field becomes strong enough so that there is no further diffusion, then this electric field will be one value, okay, and this electric field will stop the further diffusion. Now what will this electric field do? This electric field will help in diffusion of minority charge carriers, though it is not shown over here. In the p region, there are not only holes, there are some electrons also, black dot electrons also, very few, but they are electrons. Okay, these electrons will now be attracted by this positive charge, and there are some minority holes also in this region, holes, okay, some small holes also there, very few, and these holes will be attracted by this negative charge. So after the electric field is set up, okay, equilibrium electric field is set up, there is no diffusion of the majority charge carriers but the diffusion of minority charge carriers, because the electrons this side will be attracted by the positive charge and the minority charge carriers also will be attracted by the negative charge. Because of that, there may be diffusion due to the minority charge carriers. Now this region, we call it depletion region because this region doesn't have any free or mobile charge carriers. This plus positive ions and this minus negative ions are fixed or immobile ions. Okay, they cannot move. Only the electrons and holes can move. So this region in the junction is a region of the fixed positive and negative ions. That is, this region is depleted of mobile charge carriers or the free charge carriers. Therefore, this region we call it depletion region. And this width of this depletion region is of the order of 10 to the power minus 6 meter. And the potential difference, since there is an electric field set up between the positive and negative charge, since there is a positive and negative charge, there will be potential also set up between them. The potential difference which is developed across this depletion region is called potential barrier. And the value of this potential barrier is around 0.3 volt for germanium p-n junction and 0.7 volt for silicon p-n junction. Potential difference again depends upon the dopant concentration in the semiconductor. Dopant means how much of the pentavalent over here and how much of the trivalent over here you have added. From there also it depends the potential barrier. Okay, and potential barrier also depends upon temperature of the junction too. But that is the concept of potential barrier, the potential difference which is developed across the junction. Let's try to understand flow of current across the junction diode. So in the absence of any external battery, here there is no battery, some of the electrons will have sufficient energy from n region to cross the junction, and holes also have the energy to cross the junction. But and against this electric field, this we call barrier electric field, and because of that they should keep some current. Okay, because of the flow of majority charge carriers from n region, that is electrons moving across the junction and holes moving across the junction, they should give some current, but this current will be exactly balanced by the current due to the minority charge carriers. So this internal electric field will help the minority charge carriers, that is electron from p region to cross the junction and holes from n region to cross the and the holes from the n region to cross the junction. Because of that we get the minority current due to minority charge carriers. So current due to majority charge carriers will be exactly balanced by the current due to minority charge carriers, and current direction is always from positive to negative. So majority charge carriers are holes and minority charge carriers are electrons over here. So holes moving towards this side, that means current is towards right. Now here the minority charge carriers are holes, so holes moving towards this side is the current direction is opposite. So current due to majority charge carriers are opposite to the current due to minority charge carriers. So in the absence of electric field, both of them become equal. So once they become equal and opposite, the net current to the p-n junction diode is 0. So in the absence of any battery, there will be no current in the p-n junction diode. Therefore, to get certain current, you have to bias the junction. You have to do the biasing. That means we have to add an external battery to this p-n junction. So you can see over here, we have to add some external battery to the p-n junction. There are two ways of adding external battery. One we call forward biasing. What is forward biasing? A junction diode is said to be forward biased when the positive terminal of the battery is connected to the p region and the negative terminal of the battery is connected to the n region. So whenever this system of connection is there, you can say this is forward biasing. So in this situation, what happens? So positive terminal is connected towards p side and negative terminal is connected towards n side, and the direction of the electric field will be from positive to negative. So this will be the direction of the electric field, which is opposite to the internal electric field. Okay, so this external electric field does what? This external electric field helps the more number of holes to move across the junction, or more number of electrons to move across the junction. Okay, so more number of holes and electrons will recombine in the junction and they will finally vanish. Once they recombine, they finally vanish. Once electron and holes recombine, for each recombination of electrons and holes, the covalent bond over here close to the in the p region close to this battery terminal will be broken. Suppose one holes come this side and one electron come this side and they recombine. Once they recombine, the covalent bond here will be broken and it will again form one hole and one electron. An electron will go towards the positive terminal of the battery and the holes will again move towards the junction. Okay, that will happen. As soon as the holes and electrons recombine, this will happen. Again, from when this is happening, electron from the battery will go towards the N region to fill up the space of this electron which has recombined already with the holes. Okay, I'm telling you what's happening again. So these holes, because of this external electric field, is moving towards the junction and this electron is moving towards the junction. Once they recombine, for each recombination of one electron and one hole, there will be one hole and one electron generated in the p region closer to the battery terminal over here, and the electron which is generated will move towards this side, towards the positive terminal of the battery, and the holes which is generated over here will start moving towards the junction. Okay, and since this electron has combined with the hole, so there is one less electron. To fulfill this less electron space, one more electron will be generated from the p region, from the negative terminal of the battery, and go over there. So this way you can see there is a flow of the electron over here, and because of that we get the current. Thus we can see there is a motion of the majority charge carriers over here. The holes moving towards from the p region towards the n region, and the electrons moving from n region towards the p region. So usually we are getting the current due to the movement of the majority charge carriers. Okay, so in forward biasing we get the current due to majority charge carriers, and this current we call it forward current. But there will be some movement of the minority charge carriers also, like electrons in the p region will also move towards the n region because of some barrier electric field. Okay, but the current that we are getting due to the minority charge carriers are very small, that can be neglected. Okay, in forward bias junction there is one more important factor which is happening. So here the external electric field provided by the battery and the internal electric field is in the opposite direction, so net barrier potential would be smaller. Okay, because E minus EI, so net barrier width will be smaller. So here what is happening, the depletion region width is decreasing here in case of forward biasing. Okay, so depletion region decreases means there is a less resistance to the majority charge carriers. So in forward biasing what happens, the junction diode offers very low resistance to the forward bias, okay, to the current in the forward bias, because depletion region decreasing, so more number of majority charge can easily move across the junction, so resistance to the flow of current is less in forward biasing. Let's try to understand the concept of reverse biasing. Reverse biasing is similar, the only difference is that now the p region of the p-n junction diode is connected to the negative terminal of the battery and n region is connected to the positive terminal of the battery. That's the main difference. Okay, so because of that you can see now the electric field will be directed from positive to negative, so this will be the direction of the electric field, and internal electric field is also in this direction only, so both of them are in the same direction. Because of that, the barrier electric field is more now. Okay, this side is your positive charge, this side is your negative charge, and the region is again more, the depletion region increases now. Okay, because of that the holes will not come towards the junction and electrons will also not be able to come towards the junction, they will be pushed away, they will go in the opposite direction. Okay, so they will not recombine. As a result, we don't get the current due to the majority charge carriers because holes are not being able to move across the junction, or even the electrons from the n region. So usually in the reverse bias we get the current due to the minority charge carriers, which is very small current. So the depletion region is increasing, there are some few electrons are there as minority charge carriers. These electrons will be attracted by this positive charge depletion region, and this will also be attracted by this negative charge depletion region. As a result, we get movement of the minority charge carriers across the junction, and we get a small amount of current due to minority charge carriers. The reverse current is very much temperature dependent. That means now reverse current we are getting is mainly due to the minority charge carriers. Okay, so minority charge carriers are the electrons in this region and holes in this region. So the number of electrons and number of holes which is there in the p region and in the n region, depends upon temperature. More is the temperature, more number of minority charge carriers will be generated. If more number of minority charge carriers will be generated, more will be the reverse current. So reverse current basically depends upon the temperature of the junction. Okay, so here the applied electric field from the battery suppose the internal electric field. Because of that, width of the depletion region will become more, and therefore here there is a high resistance to the flow of majority charge carriers. So majority charge carriers will almost give no current because there is a high resistance. These are the facts that you have to keep that in mind. Now there are certain things also you have to keep in mind. So this is the PN junction diagram wise you understood. Now PN junction symbol is this one. This is the symbol of PN junction. One triangle and one line you can draw. This stands for P type, this stands for N type. Okay, so whether this is forward bias or reverse bias you have to check. So this is minus 2 volt, this is minus 3 volt. Now which was is more negative? Minus 3 is more negative. So you can see minus 2 is less negative compared to minus 3 because of that, and minus 2 is less negative than P minus 3, therefore P is connected to minus 2. So this is example of forward bias. Again you can see plus 3 is more positive than plus 2, and positive is connected to P region, and plus 2 is not negative but it is less than plus 3, and less value is connected to N type. So this is also forward biased. So P region is connected to plus 2 volt and N region is connected to 0 volt. So only thing you have to understand is that the P region has to be connected to the higher potential and N region has to be connected with the lower potential. So P region is plus 2 and N region is 0, so therefore it is a forward bias. P region is plus 3, N region is plus 2, therefore it is a forward bias because higher potential is connected to P region. Similarly, minus 2 P is higher potential compared to minus 3, therefore the first picture is also the example of forward biasing. Next, let's try to understand voltage current characteristics curve of PN junction diode. Okay, that is forward bias characteristics and reverse bias characteristics. This is important here. You can see over here this PN junction is a symbol for PN junction. You don't have to draw this kind of picture, you just draw PN junction like this. The positive of the PN junction is to be connected through the rheostat to the positive of the battery, and the negative has to be connected to the negative of the battery. Okay, this is a voltmeter. So this is a forward biasing of the PN junction diode. So what do you understand by the forward biasing characteristics? Now what we try to increase the voltage of this battery and try to see what happens to the current through the PN junction. You can see over here we have drawn the forward bias characteristics graph. So on the y-axis we have the forward current, on the x-axis we have a forward bias voltage. Forward bias voltage means positive of the battery is connected to P type and negative is connected to the N type. So initially, as we are increasing the voltage from 0, 0.1, 0.2, current is there slightly, there is a current increasing very slowly. Okay, and till 0.3 volt the current is there almost constant, increasing very slowly. But as we reach to the 0.3 volt, the current starts increasing rapidly here, you can see. Okay, so this is interesting here. So as we are increasing the voltage, initially the current is not increasing that much, it is increasing very small. But as a particular voltage is reached, 0.3 volt, then the current increases rapidly here. 0.3 volt is for germanium. Okay, why this is happening? So if you remember this picture of forward biasing, let me show it to you here. So when this is the direction of the external electric field because of the battery, we can say external voltage. This is the internal voltage. When internal voltage for the germanium is 0.3 volt, potential barrier is how much? 0.3 volt. If the external potential is also 0.3 volt, then 0.3 will be 0. There is no potential barrier. If there is no potential barrier, then the majority charge carriers will easily pass to the junction. Because of that, there is a rapid increase in the current. Initially, suppose the potential barrier for germanium is always 0.3 volt. Suppose if I apply 0.1 volt in the battery, then the net potential barrier would be 0.3 minus 0.1, 0.2 volt. So there is still a potential barrier. Because of that, current will not be that much, because majority charge carriers are still finding it difficult to cross the junction. But whenever the potential barrier, which is in this direction, 0.3 volt, is exactly equal to the potential of the battery, that is 0.3 volt, so that the net potential is 0, not potential barrier is 0, that means more number of the majority charge carriers will cross the junction and we can get the rapid increase in the current. So this is the reason that at 0.3 volt for germanium 0.3 volt for germanium p-n junction diode, we are getting the high amount of current. Okay, this is the forward biasing characteristics diagram. Is very important, you should check this diagram. Next, reverse bias characteristics. Here also we try to find out what happens if the increase the voltage in case of reverse bias p-n junction diode. So here positive of the p-n junction diode is connected to the negative of the battery through the rheostat, and positive of the battery is connected to the negative n-type semiconductor. So here as we are increasing, you can see, because this voltage we are increasing, we take it in the negative direction, reverse bias, we can say reverse bias and reverse current. So as we are increasing the voltage from 0 to -2, -4, okay, the current initially is increasing very slowly. Here you can see almost same, but at a particular voltage, here you can see almost at -10 volt, the current increases very high, it increases rapidly here. Okay, it's just like forward bias also, but it's a little different. So why this is happening? This is happening because of the efficiency breakdown. What is efficiency breakdown? See, reverse bias is if you increase the reverse bias, here we have increase up to what value? Here we have increase up to -10 volt. So if you are increasing the reverse bias to very high voltage, then what will happen? Then minority charge carriers will gain more amount of kinetic energy. If they gain more amount of kinetic energy, you can see over here, these minority charge carriers, if they gain more amount of kinetic energy, in this case the charge carriers are electrons, they collide with the atoms and they break the covalent bond. Once they break the covalent bond, they will create more electrons and holes. Okay, so because of this, again those electrons and holes collide with the other atom, and they will create more electrons and holes. So usually what is happening, these high energy minority charge carriers will break the covalent bonds near the junction, so that they will produce more electron holes, and this cumulative, again these holes and electrons are accelerated and they produce in the same way the other electron and hole pairs. This process we call it cumulative and avalanche of the electron hole pairs. Okay, this reverse current then increases very abruptly because more number of electron hole pairs are generated very fast, and because of this electrons and hole pairs, we can get the excessive current, okay, due to the flow of minority charge carriers. The reverse bias voltage at which the reverse current increases abruptly is called breakdown voltage. This is the voltage at which is the reverse bias voltage at which the current increases abruptly. This we call it breakdown voltage also, or general voltage also, you can say. You can call it breakdown voltage. Okay. Let's try to understand p-n diode as a rectifier. A rectifier is a device which converts the alternating current or voltage into direct current. So we have to convert this AC into DC. So p-n junction diode is used for that. How does the p-n junction diode converts the AC into DC? Let's try to find out. So for this, let's say in this picture, let's try to understand. So this is the AC input or AC input voltage. From here the AC is coming. Okay, now we want to convert this AC input voltage or current into DC. So first I make it pass through the transformer. This is a coil, and there is a soft iron rod, and there's another coil. Okay, so this is a step up transformer. So a step up transformer is doing what? It is increasing the input AC voltage into higher value. Okay, therefore we use a step up transformer here. So this is not that important here, it is just increasing the AC input voltage with the help of transformer. Now you can see this S1 is the one terminal and is connected to the p-n junction diode, and there is a output over here, Here we are trying to find out the DC component of the AC component voltage, and there is one more terminal S2, okay, which is connected to RL. So as the AC is made to pass to the transformer and is made to pass to the PN junction diode, you should convert the AC into DC. Let's try to find out how. The only concept that we're going to use is this. For PN junction diode, the resistance will be very low if it is forward biased. That is when P side is connected to the positive terminal and N side of the PN junction diode is connected to the negative terminal. And PN junction diode will have very high resistance when it is reverse biased, when PN junction diode is reverse biased. That means it will not conduct when it is reverse biased. PN junction will conduct when it is forward biased. Based on that concept, we try to understand this PN junction diode as a half-wave rectifier. So what is AC input voltage? So this is the signal AC input voltage. AC means changing with time. You know already, this is AC input voltage. So let's say this is a positive half cycle, this is a negative half cycle of the AC input. During the positive half cycle, that is during this time, up to T by 2 time, during the positive half cycle, let's say S1 is positive and S2 is negative. Okay, then this S1 is positive during the positive half cycle, therefore positive is connected to P type and N type is connected to the negative terminal, and this is forward bias. If this is forward bias, then PN junction diode will conduct and the positive half cycle will pass through the diode. But during the negative half cycle, this S1 terminal becomes negative and S2 terminal becomes positive. So negative is connected to the P type and positive is connected to N type. So now this junction diode becomes reverse biased. Because of that, for the reverse current, negative half cycle, no current will pass through the diode and we will not get anything on the output. Again, for the positive half cycle, this becomes positive, this becomes negative, and this diode becomes forward biased. Because of that, the current will pass through the RL and we can get the output, voltage or current. So as a result, we are not getting the current or voltage in the negative half cycle. So we are getting current only due to the positive half cycle. So this way we can rectify we can convert the AC into DC, alternate voltage into direct voltage or current by using a PN junction diode. Okay, this is a half-wave rectifier because it can only rectify the half of the input cycle. This is a full input cycle. It can only rectify the first half. Second half is gone. Okay, it's wasted. So we don't get any output for the second half cycle. We can get the output for the first half cycle. Therefore, PN junction diode is a half-wave rectifier. This is diagram, and this input and output is important from here. So PN junction diode as a full wave rectifier. So here again, let me see the construction. So here there is a AC input voltage which is made to pass to the transformer. This is coil and this is soft iron and this is again coil. So here S1 and S2 are again two terminals, but here instead of using only one PN junction diode, we are going to use two PN junction diode. Okay, and these are meeting together over here. This PN junction diode and PN junction diode wires are meeting together over here, and here in between we are getting the RL. We are using finding the output across RL, and this is connected in the center. So during the positive half cycle, during this positive half cycle, this S1 is positive and S2 is negative. So S1 is positive means P type is now connected to the positive terminal, N type is connected to low voltage, 0. In this situation it is 0, we can see. So this is your center tap. Okay, so during the positive half cycle, this S1 is positive, this one is 0. Okay, and there is no connection over here because during the positive half cycle, S1 is positive and S2 is negative. Negative means this PN junction diode is reverse biased, so it will not conduct during the positive half cycle. Only this diode will conduct, and we get the current like this. Okay, like this we get the current. Because of this we get the output like this. And during the negative half cycle, S2 is negative. S1 is negative, but S2 is positive. So S1 is negative means this will be reverse bias. So this will not conduct, so no current will pass through this. But this S2 is positive and this will conduct. Because of that we get the current like this. And again we can get the output. So because of the negative half cycle we can get the output. Because diode D2 conducts, diode D1 doesn't conduct. Again for the next positive half cycle, this is positive, therefore this is forward bias, diode D1 conducts, and because of that we get the current. But this is negative, therefore diode D2 doesn't conduct, we don't get any current. Okay, again negative half cycle, and during this time this is negative, therefore this doesn't conduct, this is positive, therefore this conducts, and therefore you get the output. So this way, in this kind of construction, we are getting the output for the full input cycle, input voltage. As a result, this is called the full wave rectifier.